So 9.1, it introduced a lot, but we're only in pre-cal. So even though it introduced a lot, it even introduced you to what I would call limit notation, L-I-M. I always do a cursive L because it separates it from like a 1 or Roman numeral or whatever else you might think of straight line, an absolute value. It introduced you to limit notation, which is kind of important. But for the rest of chapter 9, we are not going to talk about all different types of sequences in series, including the ones that you saw just now, 1 over n and 1 over n squared. Instead, we're going to talk about 2 specific types of sequences in series. In 9.2, we're going to talk about arithmetic or arithmetic sequences. And in 9.3, we're going to talk about geometric sequences and series. When you see partial sums, we're talking about series. But a a finite series as opposed to an infinite series. So if you want to write finite series, so we're only talking about 2 types. We could not get really more general than that without getting you guys to Calculus BC first. So, arithmetic and geometric. I like saying arithmetic because that's what it looks like. I know some people will say arithmetic, but whatever. There we go. What's the difference? Huh? What's the difference? What? Oh, you got it? Oh, I didn't realize that's what you got. That's okay.
That worked for one more.
Woo! All right. Nicely done. At least it didn't like implode. Explode? Anyway. Probably not. Might just overheat and turn off and then just be like, nah, I'm dead. Like phones in the sun. I think it would just, well, eventually it could say overflow, but that's only if the number's too big, so I bet it would just keep on thinking until the battery dies, technically. Okay, arithmetic sequences, going from one term to the next. As you guys read what's going on, the difference is constant, and I don't just mean difference as in like, oh, hey, what's the difference? The difference as in the mathematical term of taking one term and subtracting the prior. Difference, that's a mathematical term for subtraction, right? Sum would be a mathematical term for addition. So if you subtract any 2 terms, you're going to have a D, because to get from one term to the next, all you got to do is add D. Common difference, that's D. Special type of sequence, where to get from one term to the next, you just add. So therefore, you were supposed to have that written down from last night. Here we go. The sequence whose nth term is 4n plus 3. Huh. Nth term, doesn't that mean a sub n, guys? It's asking us whether or not this is an arithmetic sequence. How do we know? Yeah, if worst comes to worst, plug in numbers and say, okay, fine, who is this guy? Who's A1? Who's A2? Who's A3? We could keep on going, but we'll just start there. 7, then. How could you look at the nth term formula and actually figure out that this is an arithmetic sequence also? How could you look at the formula? 4 times 1 plus 3, 4 times 2 plus 3, 4 times 3 plus 3. There's a constant. The plus 3 always stays the same. The 4 always stays the same. Where is the change happening? The multiplication. Wait, what happens when you multiply by 1 higher power of a number? Sorry, multiply by 1 higher value of a number. You're really just adding an extra 4 every time. Look at your common difference. If you solved A1, A2, A3, don't you see the plus 4, plus 4, plus 4? I was just trying to give some of you guys a mental clue. That's always going to happen when n is just being multiplied by a value. So, is the first one arithmetic, arithmetic, whatever? The answer is yes. How about the next one, though? The first one is yes, and the reason that we could prove that, or the reason that we could state that, is we can say D is equal to 4. How about the second one? N squared, it shows us a sequence, 1, 4, 9, 16, 25, 36. It has a pattern, but wouldn't the addition be plus 3, then plus 5, then plus 7? Is that constant? No. Pattern, but not constant. So is it arithmetic? No, there's no common difference. Does that make sense? Pattern, yes, but not a common difference. Ready, set, find me the 20th term. Ready, set, find me the 20th term. No. Because we're trying to find, if you notice at the top, discovery, we're trying to find a formula. So could you go all the way to the 20th? Yeah, you can make 19 jumps if you really want to, I guess. 16 jumps, technically. Making 16 jumps, have fun with it. Or maybe there's a way to jump there faster. Who's gotten there? Ooh, we have one. Who's trying to remember a formula from last year? Who's trying to make up a method right now? Yeah, make up one. That works. What's the common difference? Negative 5, right? Minus 5 or plus a negative 5? Okay. So we're jumping by subtracting 5 or adding a negative 5, subtracting 5, adding a negative 5. Question. Couldn't we rewrite a little formula for this to be 2 plus negative 5 times 3? Right? Because to get from 2 to the 4th term, right? A sub 4. To get from 2 to a sub 4 to the 4th term, I needed to add 3 jumps of negative 5. So how could I get from the first term to the last term, aka a sub 20? Using that equation. Times what? Not times 20. To get to the 4th term, how many jumps did we do? To get to the 4th term, we did how many jumps? I see 3 jumps, don't you? So to get to the 20th term, how many jumps are we going to do? 19. So therefore, I could say, oh, is an a sub 20 just going to equal 19 jumps of negative 5? Which would end up being negative 93? 5 and 4 are 90. That's 95. Negative 95 plus 2. Could you have in your calculator done negative 13, minus 5, minus 5, minus 5, minus 5, minus 5? Wait, how many was that? But could you have done it? I suppose. But can't we do repeated subtraction just by multiplication of how many jumpity jump jumps? Ooh, jumpity jump jumps, recursively. So does it kind of make sense why there's a formula for arithmetic sequences of how to always get the a sub nth term given the first term and given a common difference d? That's the formula. But doesn't the idea make sense? If you're doing repeated jumpity jump jumps of a common difference, well, it's just multiplication. And if you think about it, you have 5 fingers and 4 gaps in order to get from a first to a fifth, from a first to a 10th, from a first to a 20th. There's going to be 1 fewer jump that you have to take. To each his own. Algebra and number tricks. But for some of you that don't like algebra and number tricks, I guess you could just do lots of memorizing on formula cards. It's okay. It'll work. Quizlet. Let's go. This is called the formula for the nth term, jumping to a term in a sequence separated by commas. Are we tracking? If I were you and you were a highlighting person, I would highlight, I would star, I'd make a big deal out of this guy because you're going to need to have him memorized by the test or understand the idea so well you can come up with the formula on your own when prompted. Ooh. Okay, we got him? Ready, set, and? So, have fun with this guy. Shouldn't make you think too outside of the box. Wasn't too bad, right? Because nth term, doesn't that just mean they want a sub n? Arithmetic sequence, doesn't that mean I can use my cool formula? First term, doesn't that mean a sub 1? They didn't tell me n, so okay, I'll leave it unknown. And the common difference is 3. Now, if you wanted to be snazzy, could you go ahead and simplify that to be 3n minus 1? You could. But isn't it technically just plugging in to begin with? Because you would distribute 3n minus 3. Negative 3 plus 2 is negative 1. So you could simplify. But it could start with the formula that we just wrote down. Does that make sense?
Yes, it does.
Thank you. Need some sort of affirmation. Don't we all? Okay, so what if I wanted you to add together all the numbers from 1 to 100? It might seem kind of random and weird. Gauss, but close. We did say Gaussian when we were trying to, or Gaussian when we were talking about elimination. The story goes, I forget how old. Is he 2nd grade? The story goes, well, 2nd grade is not exactly in a traditional school, but that's okay. When he was little, and he was in school, the class, this mathematician at the time, he was just a little kid, maybe a bratty kid. The story was that the class was totally acting up and the teacher was getting really frustrated, needed a bit of silence, needed a bit of quiet, and so was finally like, okay, fine, get out your slates, whatever they were writing on. Add all the numbers 1 to 100, and all the kids started, oh, okay, fine. Teacher sat down at the desk being like, I finally get some peace and quiet. I've been working for a little bit, doing something productive, and as soon as he or she, probably a he in those days, working, little Gauss came up, put the slate down, had the answer, and sat down. Teacher was super frustrated, thinking the kid was just being a brat. Probably wouldn't have used that word back then, but that's okay. Hadn't actually worked out the problem yet. Started working out the problem, figured out the little punk was right. He had a method to his madness, and it did not have to do with literally adding 1 plus 2, and then plus 3, and then plus 4, and then plus 5, and then plus 6. His final answer ended up being 50-50. How'd he get there? Kind of? What were you saying? Almost 99 plus 1. What did he figure out? It wasn't generalized until much later to be for any arithmetic sequence. Ooh, it's really just an arithmetic sequence. But what he figured out is if you add 1 plus 100, because he wanted to be done faster, what does that end up getting you? What happens if you add up 2 and 99? What happens if you add up 3 and 98? What's going to happen to every pair of numbers as you narrow down the problem? How many 101s were there? 50. What do you end up getting when you multiply 101 by 50? John's was okay, except what was the problem with it? You've had to do 1 plus 99 and 2 plus 98 and 3 plus 97. The numbering would be a little bit off. Does that make sense? Because you would only have 99 numbers that you're adding. And so the hundreds would be easier to accumulate. But would you have 50 hundreds? No. How many hundreds would you have? 49? Yeah, you'd have 49. they'd have like a random 50 stuck in between without a pair. So 4950, and then you have to add the 100, so then you need to get 5050 also. So it would work, just a little bit messier in the sense of having to keep track of everything as you narrow it down. Does it possibly make sense then why the formula for, which was generalized later, but why the formula is what it is? Wait, what? What's a sub 1? First term. What's a sub n? Nth term. Good. So if I'm trying to find the 100th partial sum, like this one, the 100th partial sum, I would have added the first term plus the 100th term. Now here's the struggle. In adding the numbers 1 to 100, it was super easy to find the 100th term. It was 100. But in a different arithmetic sequence, could it be harder to get to the 20th, 50th, 100th term if they don't give it to you? Oh. So quick heads up on this guy. Sometimes, if you can't just automatically figure out what the last term is, you might need to solve with a sub n equals a sub 1 plus n minus 1 times d first. Sometimes you won't be able to plug straight into the nth partial sum formula because if it's not obvious what the nth term is, you can't just add the first and the nth super easy. You have to go find the 20th term, 50th term, 100th term. This one was easy though. He knew what the last term was. Add the two, the first and the last together and say, hey, multiply that by however many terms there are divided by 2. So in this case, it's exactly what happened. Adding the 50 terms, sorry, I keep on writing 50. The answer is the 100 term. Two of them are going together with the first term plus the last term. So 1 plus 100 was 101, and 101 times 50 ends up being your 50/50. If you're a highlighting starring kind of person, should you probably highlight star? Should you maybe even highlight star the note that says, hey, if they don't give you the nth term, you're going to have to find it with the aforementioned formula in order to solve? Sometimes you need to solve with, W with a slash, quick little way of saying with a sub n is equal to a sub 1 plus, it's just the formula from right up above. You could draw a little arrow, technically, if you want. Sometimes you need to solve with the nth term formula or the a sub n formula. Ready, set, play. The first one was, look at that, they gave you the ending term. How nice. But if you try Gauss' method, I think it will work. 1 plus 19 is 20. 3 plus 17 is 20. 5 plus 15 is 20. Oh, wait. Don't want to give it away too soon. Divide what? Colby, what's up? Yeah, the division just has to happen somewhere. You could think of averaging it, I suppose, and then multiplying it by how many numbers. The concept's a little bit trickier that way, but yeah, it's okay. Did you guys figure out this is the 10th partial sum? Or there's going to be 5 groupings when you put 2 and 2 together? Wait. I divided by 5. I was supposed to divide by 2. Adding 1 plus 19 together is 20. There are 10 terms total, so that's n, and n divided by 2 is going to be 5. 5 times 20 is 100. Okay, hold on. Let me show you the peek at how much more through this section is supposed to be. Our goal is to finish the whole thing. Hey! Psh, you don't need me to do a word problem for you. Ready, set, tackle section 9.2 over the weekend. Finish up 9.1. Have any series things you might have got stuck on, come to me with questions. We'll grade both of them on Monday. Sound good? Oh, no, did you really? A 100,000?
Not that one.
Oh. What'd you get?
1.61492.
Woo! All right, cool kids. Happy Friday. Happy weekend. You have 25 seconds, 22 seconds to get things ready. Ooh, right on time. Ryan Nix, Mr. Prats needs to see you. You can head on up. Oh, is it today? Wait, I don't think so, yeah? Trying to trip me out.